Oh well, hello, those listening. I'm David. I'm coordinator of the Maths Learning Centre. At this stage I'd normally show my face on the camera, but it's pointing at the wrong thing, so I won't do that. Could climb on the table, I suppose, and look upwards, but I don't feel like it. This is Semester 1 2019. It's a revision seminar for Probability and Statistics 2. Got pretty luxurious because we've got several days until this exam, which is okay, better than the last one I did, which was on the day before the exam. No, it was 2 days before. It was all right. I've been given some requests. I'm going to need to really rely on the people who are here to give me examples to work from, because I don't have like a textbook or any of that sort of thing. So let's go. Okay. Even those things that I listed before, which were various proofs of things, maybe it will be a miscellaneous problems sort of session. I don't know if I can organise things that already exist unless after the fact. So I can look at the order statistics first because it's the one I know the most. So order statistics, and it's really not, the order statistics I suspect are not, the concept of them is probably not the problem, it's the distributions of them that's the problem. But let's think about it. So my understanding of this goes is that you have, does your lecturer use Y instead of X? So we've got these random variables, and usually they're independent and they're all the same distribution as each other. I think there's an abbreviation for that, IID. Okay. Oh, and you call that identical, wouldn't you? All identical distributions, and that's what the IID stands for. Okay. Okay. The idea being, I think that these are all measurements of the same thing on usually different individuals. So when you use it in statistics, it'll be like, oh, I've got a class of 70 students and I'm going to record their grade or their height or whether they believe in something. So you've got you have a measurement on several individuals. They could be people or they could just be objects. And you're going to assume they're all independent, they all have the same distribution. And then what you're going to do is your statistic is going to be the whatever one of them when you put them in order. So you're going to have like U, say, like the third biggest YI. Is there a notation for this?
Yeah, if you use like brackets for the Y brackets for the subscript.
Okay, so that's like square brackets, round brackets?
No, so around the subscript you have the bracket. Yeah.
Yep. So the Y1 is the maximum, is it? Or is it the minimum? Okay, so this is actually the third smallest one. Okay. Okay, that's the notation. And so you might have, for example, the minimum of all the YIs is Y1, like that. Okay, cool. Just making sure I've got the notation down. So if you want to talk about something, that's why we have notations, so that we can make it easier to talk about. And the question we're really interested in is, what is the distribution of this thing? Okay, cool. So I want to think about that for a second. Okay. And so okay. Sure. So when we talk about distribution, I'm thinking that different sets of like 10 y's would have different minimums, and we're interested in what all the minimums could be and how likely they all are. Okay. So just want to make sure I got a handle on what's going on here. So I could take could take 5 dice and go, the minimum is 2. Just a second. And also 2. And 1. And 1. And 4. Wow. Cool. And 1, and actually I guess we probably really want something like this. I'm not going to be good at drawing boxes for very long. I'd expect it to be 1 rather often, I'd say. 1. House rules, roll it again if it goes off the table. Wow, okay, so our distribution is mostly 1s and 2s. So this is the distribution we're wanting to find out about. This thing here, how often do each of these numbers come up as the minimum? It's still possible to get 6 as the minimum, but you would have to roll all 6s to do that. That would be extremely rare. Still 2. I really want a 3. Yeah, anyway, that's the idea, and we're interested in what all these probabilities are. Okay, cool. Rightio. Sorry? What? Okay, right. So, can I do it with dice and see what I can figure out? Let's do that one. Distribution of the minimum. I don't know I have no idea what's going to happen here. I mean, what we'd actually have to do is we'd have to figure out the probability of all of these things. So each of those numbers, and let's call it, so the idea is that y1, y2, y3, y4 and y5 are the 5 dice results, and we want distribution of y1, which is the minimum. Okay. So to say we want the distribution means we want a description of what all the options are and how likely they all are. So with a discrete one, it would be useful to list what all the options are and then find all of those probabilities. So is there a terminology or a symbol for the set of all the possible outcomes? Sorry? Omega? I think omega is the set of possible outcomes for the They're not the numbers. Am I wrong about that? Just S? S is the sample space. I think omega is the events that can happen, and S is the numbers that can happen. Could be wrong. Sorry, I don't know.
We just take our state space and then we just label the state space with numbers. Yeah.
All right, so I'm just going to say the possible outcomes and not have a symbol for it. 1, 2, 3, 4, 5, 6. They're all the only things that the minimum could possibly be are the things that can come off of a die, so that's good. And we want the probability of each one, and I don't think we're going to be able to find a formula for it. I think we're just going to have to do them one at a time and see what happens. So, okay. Or we could, I don't know. Well, the probability that y1 is 1 is the probability that the minimum of all of those is 1, which is the probability that at least one occurs. At least one occurs. That's the probability that... Probably that at least one of the yi's is 1. Because if none of them are 1, then the minimum can't be 1. Because it has to be bigger than 1. Okay, so that would be the opposite of the probability of none of them being 1. So at least one of them being 1. That could be the number of them being 1 is 1, 2, 3, 4, 5, or 5. And the only one that isn't covered by that is none of them being 1. Okay. Well, that's good. I can do that one because that's the probability 1 minus the probability that y1 is not 1, y2 is not 1, up to y5 is not 1. And they're all independent, so I can separate those probabilities into separate probabilities. Okay, and I know the probability of not being 1, it's 5, 6. Which is whatever that is. I don't know what 6 to the power of 5 is. Okay, that's what it is. 4 decimal places. Cool. So it's actually nearly 60% ones. So I actually really do expect there to be a lot more ones than anything else. Okay. Probability that y1 is 2. Okay, that's the probability that the min is 2. So it's not allowed to have any 1s. And it has to have at least 1, 2. But let me just do the other one. I switched it around to the opposite to figure it out. So maybe I could do that as well. The probability of getting everything greater than or equal to 2, actually just a second, that's all yi's are greater than or equal to 2. And there has to be at least 1, 2. Oh, crap. Okay. Well, the opposite of them all being greater than or equal to 2 is the same as not having any 1s. And the opposite of them all being, and not having any 2s or 1s, is the same as being strictly greater than 2. Right. So just a second. Just a sec. We already know how many ways there are for the minimum to be 1. So if the minimum was 1 or 2, that would mean that the opposite of the minimum being 1 or 2 is everything being more than 3, or being 3 or more. Okay, so we would need just a second. I'm just going to figure something else out. So the probability that the minimum is less than or equal to 2 is 1 minus the probability that the minimum is greater than 2. 1 minus the probability that the minimum is greater than or equal to 3 because it's discrete. So all of them would have to be greater than or equal to 3 for the minimum to be greater than or equal to 3. Because if any of them was less than 3, the minimum would be less than 3. So I need I need all the yi's are greater than or equal to 3 to do that. Let me just check that they actually work directly. If they're all greater than or equal to 3, then the minimum can't be 1 or 2. So therefore the minimum has to be greater than or equal to 3. And if the minimum is greater than or equal to 3, then that means that the smallest one is at least 3. And so they're all greater than or equal to 3. Good, they do match up. And so that's the probability of 1 minus the probability that y1 is greater than or equal to 3 times the probability that y2 is greater than or equal to 3. Like that. Cool. And so therefore these, and they're all the same because they're all the same same distribution. And greater than or equal to 3 is 3, 4, 5, 6, 4 out of 6. Cool. Yes, there's only 5 of them. Okay. And that's probably being less than or equal to 2. So if I took off the probability of being equal to 1, that would give me the probability of being equal to 2. Okay. Because this is only 1 or 2. So that's 1 minus. Beautiful. Awesome. Which is whatever it is. Five, 6 power of 5, 6. Okay. So it's about a third as likely as the 1. Right. And so I reckon I could just keep reusing that same reasoning all the way along. So I could say that the probability that y1 is less than or equal to 3 is 1 minus the probability that y1 is greater than or equal to 3, which is 1 minus the probability that all the yi's, greater than or equal to 4, greater than 4, which is 1 minus the probability of y1 being greater than 4, it's 1 minus 4, 5, 6, 3. So the 5, and so therefore the probability that y brackets 1 is, damn it, is actually equal to 3 would be the probability that y1 is less than or equal to 3 minus the probability that y1 is less than or equal to 2, which we already figured out. It's not nearly so simple as it was before. Okay. All right. And so on. And we could figure them all out from there. I think I'm right.
Is there anything else just the second, the subtract the second one? 5 over 6, 5 over 6 and 3. Because that would encapsulate all the ones and twos.
Sorry, what's that?
So is there anything else just to subtract that one?
Oh, crap. Yep, sorry. It's the less than or equal to 2, not the equal to 2 that I want to subtract. I want to subtract this one. Yeah. Which is cool. So there's a pattern forming. Okay. And so I could continue to this to get a probability for each of them. I mean, at this rate, there's nothing I can do. I have to, it looks like the pattern's going to be this. Well, we know what this one is. The probability of the minimum being 6 can only happen if they're all 6. Which is that. Cool. Okay, that's the distribution. I think there were some useful things that happened here. I wouldn't expect someone to do this in an exam. But your lecturer could probably ask you what one of these was. Not all 6 of them, but just to say, well, what's the probability that y brackets 1 is 2? And then you would do the working that would get you where you want to go. Okay. Cool. So I think we can reuse something useful here. To figure this out, we had to do this. This flip of we had to actually use the cumulative distribution, like the probability of being less than or equal to it, to figure out what and flip that around to being, well, we need the minimum to be greater than something to do that. So I reckon we can reuse that even with a continuous distribution. So I just want to do an example with a continuous distribution and see what happens there. Is that how your lecturer does uniform distribution? Let's go. It's been really, really awful. So yi is distributed according to the uniform distribution with minimum 2 and maximum 7 for I being from 1 to 10. Okay. And y brackets 1 is the minimum of y1 to y10. Find the distribution of y1. All right. So distribution is a description of what all the options are and how likely they all are. For a continuous distribution like this one, seems reasonable that we should give either the cumulative distribution function or the other one, the PDF. Okay, PDF seems more likely as a thing that would be useful. Okay, so what did we do before? We found the cumulative one first. Let's pick a number. X. I guess before I start, the minimum can't be anything outside 2 to 7 because my uniform distribution doesn't produce anything else. So that would be 1 minus the probability that the minimum is greater than x. And for the minimum to be more than x, all of the yi's have to be greater than x simultaneously. Because if they're all more than whatever this number x is, the minimum has to be more than that as well. And if the minimum is more than that, well, that's the literal meaning of the minimum being x, is that everything's more than x. Okay, cool. And since they're all independent, I can do this. I should really say they're all independent somewhere. And since they all have the same distribution, that'll be that. So now I just need to know what the probability of y1 being greater than x is. Just give me a second. It's a uniform distribution from 2 to 7. And the x is some number in the middle here. And this has some height, that's the PDF. And this being greater than x would be, it's technically not equal to x, be this area here. But we really only want it as a proportion of the total area, so it would be this distance divided by this distance. So that would be 7 minus x divided by 7 minus 2. Okay. So the probability that y1 is less than or equal to x is 1 minus greater than x 10, which you just figured out was over 5 to the 10. Cool, so that's our cumulative distribution function, i.e. the CDF of y1 is capital F. And I guess technically it doesn't exist outside that, like it's 0 when x is less than 2 and 1 when x is greater than 7. Are we supposed to do the full details on that when we ask for these things? I guess we need to at least tell what the x could be. And so therefore, the PDF of y1 would be the derivative of that. Okay, so the 1 will disappear. 1 will disappear, the minus will still be there, power comes down, there's new power. The dividing by 5 is technically a constant, and the derivative of minus x is x. The derivative of 7 minus x is minus 1. So 10 divided by 5 is 2. Beautiful. That's what the PDF is. Luckily, those minuses cancelled out, otherwise it would be extremely distressing to get a PDF with a minus in front. Thoughts, questions at this stage? Of any kind. I really feel like doing a maximum. I feel like the reasoning would be slightly different. So were there any order statistics questions using particular distributions that felt really hard?
I don't think so. We did any of these. We just did something different.
Oh, okay.
Sure.
Let's have a look at what you did.
She just proved something.
Okay.
I just have to find conditional odds. Poisson process. Yeah, so we use like transformation of method to find it. Yeah. So there's the second page.
Oh, we did it in general.
Yeah, yeah, and like
Let's go.
the maximum and the minimum. You can have it if you want to look at it. Yeah, so we did the maximum first, then the minimum.
Yeah, so you're doing the exact same thing that I
Yeah,
did,
and
but with a general one.
Yeah, and I have an idea that maybe we're gonna have to prove this by induction in
Okay.
the exam. So that'd be cool.
Sure. You were laughing before at how easy it was for me to describe what was going on by just rolling some dice, weren't you?
Yep. How clear was it? Yeah. I was much clearer. Yeah.
Okay. So we're going to go full on general with this. So we're going to go something like that. They're in, IIDs, so independent, identically distributed. They're continuous with this CDF and this PDF. Okay. Find the PDF of the maximum yn. Yeah? All right. So this is totally the sort of thing that you could be asked to do in an exam, and you might want to find a way of coming up with a proof on the fly. Be good to remember one, but even that, I'm never good at remembering things, but I can remember at least enough of the way I went about it to get there. So let's see. Okay, so what should I call it? F sub something. M for maximum? Let's do that. I'm going to use X because I don't want to use Y because I'm going to get confused. So okay. I have a T-shirt that says, I should have worn it today. I have a T-shirt, not brackets, getting confused. I have a T-shirt that says TLA on it, which stands for a 3-letter acronym, which is what this course is full of. Okay, so, all right, so F X is the probability that Yn is less than or equal to X. So if the maximum is less than something, so in my head I've got this, if the maximum is here, then all of the y's have to be here. That's what I'm thinking. So if the maximum is less than or equal to x, then all of the individual ones have to be less than or equal to x, and that works both ways. It's very useful to not talk about the maximum being equal to x, because then you have to be sure that one of them is equal to x. But if you just say it's less than or equal to x, then everything being less than x makes the maximum less than x. Okay, cool. So this is the same as probability of all the yi's being less than or equal to x, which is the probability that y1 is less than or equal to x, which we can do because they're independent. We can separate them all. I mean, technically it's like this. Technically it's like and, which because they're independent can be separated into a product like that. Because the probability of a whole lot of events all happening at once is only equal to the product of each individual probabilities if they're all independent. Okay, and this is f of x. So that's f of x to the power of n, because there's n of them. Cool. That was easier than the minimum. Okay, and so therefore the PDF of the maximum, little f m of x, which is big F, the derivative of big F, just the derivative of that. So power comes down, power reduces by 1, but then the chain rule says I have to multiply by the derivative of that. But the derivative of the CDF is the PDF. Beautiful. We've found it. Ta-da. Okay. So now we could go all out and try and figure out what... We've done the minimum, we've done the maximum. We could try and figure out one of the ones somewhere in the middle. Like what about the second smallest? Or the second biggest? Okay. Okay. So sort of like part A. The second biggest? yn minus 1. No, actually, do you know what? I'm going to just say kth order statistic yk, and just go, let's do it all out and see what happens. Okay. So for the kth order statistic, currently our reasoning has all been based on what the maximum, like saying, well, it's bigger than all of them. And our reasoning has been based on, or it's smaller than all of them. So the kth order statistic is the kth one in order. There's yk. And then there'd be k minus 1 here that are less than it. And well, all the rest are bigger than it. So n minus k here to add up to k total. N minus k plus k minus 1 is n minus 1, and then 1 extra to add up to the full n y's. And I don't actually know which of the yi's is y brackets k. It's one of them, but I don't know which one. It could be y1, it could be y7. The dice can tell which die is which, even if I can't. So, but that might not be important. Okay. So it seems to me that f brackets k be the CDF of y brackets k. That seems reasonable. So it seems to me that f brackets k of a particular value x would be the probability that y brackets k is less than or equal to x. Which would be the probability that k of the yi's are less than x. Oh crap, this is hard, isn't it? Okay, so if your lecturer said she would use induction, if I were going to use induction, I would need to think about the pattern of how I would figure out one of these from the one before. Okay. So how would I figure out the second smallest from the distribution of a minimum? I mean, you'd need k of the... Okay. So if... I don't know yet, but let's figure it out. I'm real sure it's possible. If k of them were greater than or equal, were strictly greater than x, well, if too many of them were more than x, then the kth one couldn't be less than or equal to x. Like if you wanted the third one to be greater than or equal to 5, then if all except 2 of them were less than 5, then the kth one couldn't be greater than 5. Like the third one couldn't be greater than 5. Like, so with my 5 dice, if all of them if I wanted this to be the second one to be greater than or equal to 3, then I'd need this. I'd need at least 2 of them if I needed the second one to be greater than or equal to 3, it wouldn't matter what the smallest one was, but then everything from the second one on would have to be greater than or equal to 3. So all but one of them would have to be greater than or equal to 3, and the other one could be anything and it wouldn't matter. Yeah? Because it doesn't matter what the small... Oh, crap. So the smallest one would have to be less than 3. And then the smallest one of the rest would have to be greater than or equal to 3. Right. So, okay, just a second. And if I wanted the third one to be greater than or equal to 4, I would need both the first one and the second one to be less than that. Or it wouldn't be this wouldn't be the third one. They could also be the same, so less than or equal to 4. So I'd need... So if I wanted the third one to be greater than or equal to 4, then I'd need these ones to be less than or equal to 4.
Where one of
Well, if two of them were less than or equal to 4, and the rest of them were greater than or equal to 4, then the third one would have to be greater than or equal to 4. Yeah. And they're both or equal to's. Because if... Yeah. But we want less than, don't we? So if we want this to be less than or equal to 4, the third one, then all of the ones before it have to be less than or equal to 4 as well. And then all the ones after this have to be greater than 4. Or equal to. That would be okay. So you would need... So for the third one to be less than or equal to 4, you need the first one and the second one to be less than or equal to 4. And that's where the induction comes in. You need all the previous ones to figure out the next one. Yeah, sounds like strong induction. You might only need the one before, because if the second one is less than or equal to 4, that forces the first one to be less than or equal to 4 automatically, because it's less than the second one. Okay. Okay. So we'd need... Okay, I'm just going to write down that reasoning. So for the kth one, to be less than or equal to x. So for the kth one to be less than or equal to x, we'd need first, second, up to the k minus 1th to be less than or equal to x as well. That would have to happen as well. So what was my minimum reasoning? The maximum reasoning was easier, wasn't it? So maybe I should do the maximum end. So for the case one to be less than or equal to x, it doesn't really matter what the other ones are, they just have to be more than. Oh crap. Pretty sure no one would expect you to do this off the top of your head in an exam without having seen it before. I just want to see what the answer in the notes is. So that looks like choosing which ones it is that are going to be the small ones and the big ones. That's the probability. These are the ones that are smaller than it. These are the ones that are bigger than it. Is this in here too?
No, that's for...
Oh, that belongs to this?
Yeah.
That's f of y times k?
Yeah.
Sure.
Or not yk, but y sub k.
Y sub k.
Yeah.
Oh, yeah, okay. Oh, I get it. That's the value. I've just called that x in mine.
Yeah.
Right, gotcha. So this looks like a choosy thing, right?
Yeah, as what you said, you choose this many.
So we choose k minus 1 of them to be less, and n minus k of them to be more, and 1 to be somewhere in the middle. Is this a capital F? No.
No, there's a period. Yeah, she just gave us this thing.
All right. I can see some reasoning there, but I can't quite pinpoint how to do it.
Like in the lectures, she just explained to us what in each sort of part meant in a hand way these sort of matter.
Yeah.
And if you sub in, you can get the minimum. If k is 10 or whatever. Yeah.
Okay.
Like it looks hard.
It's looking pretty hard. There's a lot of moving pieces here. So you could choose which ones were going to be smaller than x and which ones were going to be greater than x, in which case there would be this many ways to make that choice. And then you could choose yeah, I reckon we can go there direct without using induction like you said. Partitioning all of the possible ways to get them to be arranged the right way. So you would need, so just a second, let's ignore all of that. This is literally a counting argument, the giant tree diagram. So, and we can go directly, so we could go so you would need to choose k minus 1 to be less than or equal to x and n minus k to be greater than or equal to x, which can be done in n ways. I guess you need to choose k to be less than or equal to x technically, because it's the kth one that has to be. No, I think it'll be okay. And then, I don't know which way around these are going to have to go. Because there's going to be one that doesn't matter which way it is, it just has to be, doesn't really matter. Anyway, the kth one definitely has to be less than or equal to x. So you choose which of them are going to be, and then once you've got that, each of the probabilities of doing those things are what they are. So, the probability that yi is less than or equal to x is capital F of x. The probability that yi is greater than or equal to x is 1 minus f of x. And so then I get the probabilities add up, right? You've got this many ways to get this probabilities, and you just multiply them all together to get what you want. My choice of ki's and yi is greater than or equal to x of n minus ki's, and that would be probability of doesn't matter which one. Sorry, wrong one. That's right. I'll just leave it like that. And so then we add all up those probabilities, I guess. So I have a feeling that some of them are going to be overlapping with each other, aren't they? But that's okay, because we made the choice of which ones first. It's not going to work, is it? Yeah, and I have to differentiate that, right? which is not going to come out to the thing that we just had. All right. Where were you going to go with this? This, basically, or something else entirely?
So just all the conceptual things you're saying, that sort of like, so just for the PDF, because you've got your sort of choosy thing and partitioning into 3 different groups, and then it kind of just looks like a bit like a trinomial distribution after that, where you've got like the probability of being smaller than, probability of being less than, and the probability that it is like the K. So you sort of just got like 3 different sets of trials, I guess. It doesn't really have a proof, but it's...
No, it's something like that. Yeah. Yeah. Actually, isn't there a thing with conditional probabilities, like with a joint distribution thing? Is this after we did joint distributions? No.
No, it's before.
Oh, okay. Because then, yeah, because this might be a joint distribution thing. Because with the joint distribution thing, you can go direct to the PDFs using that. Because there'd be, if I'm thinking a big tree diagram that gets to this point, there's all these conditionals along the way. So we can go that the probability that, and maybe that's why the induction comes in. Because when you do joint distributions, you can do the probability that that sort of thing. Like F. Something like that. And then it comes out to like the joint distribution, yeah. Gotcha. So you get the joint distribution of y1 equals x, y2 equals x over like that. Yeah, I reckon it's something like that. So I think the conclusion I would make at this stage is that I don't think she wants you to be able to prove it or even necessarily give an explanation of why it is. She may care about you using it, but I also have a feeling that she may give it to you. If I were her, that's what I would do.
How much does she actually give things for you to work with? How much does she expect you to just memorize? Because there's a lot of like...
Don't know, she's new this year for this course. Oh, this is where you are for everything. I did the switch over for new lecturers this year. They really shouldn't do it all in the same year. But that's every 3 years or so they
like they had the new curriculum for 1A and B last year as well. So we were guinea pigs for that as well.
And anyone who did year 12 and the year before that were also guinea pigs for the new Australian curriculum. Oh yeah. Okay. So I think I could conceivably do the second one directly, but I don't know if I want to go there. I think it seems to me that the sorts of things that she would ask in the exam would be about maximums and minimums because they're the easiest to reason with within the time you've got. That's my guess. And unfortunately, at some point, doing exams is itself a probability game. Figuring out what could possibly happen. But we have several days to try and thrash it out in the Maths Learning Centre if we want to. But I don't think it's productive to do it here. Okay. All right. Right. So there was a distribution for the order statistics. I'm just going to write down here. This is very hard. Apparently the answer is this. According to the notes. According to the lecture notes, Wish I had more space. Just a second. I'm going to rewrite that below it so that I can write it all on one line. All right, that's apparently it. Apparently it's that, which makes some reasonable sort of sense based on the argument that you're describing. Yeah. And I can believe this thing happening when you differentiated something at some point. Yeah. Actually, I reckon one of them, I think mine wasn't too bad, because these both appeared in mine. I reckon when we factorise some things out, some things cancel. Because if I had a k in mine and when I differentiate that, that'll come down to k minus 1. Because of the, and a product rule thing would mean that one of them would stay as a k. And I reckon when I factorised out, yeah, look. It's the n minus k that's bothering me at the moment. But when I did the derivative of this, it would be k, fk to k minus 1, then I'd keep that. And then I'd have an n minus k, and this would be an n minus k minus 1. And then they'd both have this thing in front of them. And so then I could factorise out the bits that had common denominators, and I reckon I'd get an f of x in one and a 1 minus f of x in the other, which when you add them together would give you 1. Yeah. I reckon we could get there from here, probably. Yeah. But I'm getting an n minus k minus 1 in mine. So I've made some reasoning mistake here that means that we don't get it right. Yeah. So I reckon there's a k minus... Yeah. All right. Okay. Sure. Because I was trying to use the same reasoning we use for everything else, which was all based on the cumulative distribution. And it has to be based on the cumulative distribution somehow for these to appear where they appear. Yeah. All right. I guess I could integrate this and see where it came from. Maybe not. I'd have to use integration by parts. And go around in circles. That's a job for another day entirely. Okay. Did you get something cool that worked?
No.
Something else entirely?
Entirely, yeah.
Do you want me to talk about it?
No, it's a sort of
Okay. So, just looking at the photos of the emails that people sent. Yep. I did get asked to talk about something with Poisson processes. I'm not sure on the details. What sorts of things were you hoping for? Before I just want to deal with the things that people asked me already. Okay. So my understanding of a Poisson process, I'm just going to do this example. So customers phone a helpline according to a Poisson process. Rate of 3 calls per minute. Okay, cool. So before I even look at the goal here, I just want to understand what's going on here. We have time, and then calls happen at various, like that, and they're spread out at different amounts. And the idea that on average, if you take a 3-minute period, on average, sorry, if you take a minute period, on average there's 3 in that minute, on average. Okay? Cool? So, on average every 20 seconds. So just a second, just let me just understand this. In a 1-minute period. I expect 3 calls, or a call every 1 minute, 1/3 of a minute. They're the same thing. Just thinking about that. And so you could try and take a particular amount of time and count how many of the calls happen in that time, and that would be a Poisson distribution. Or you could look at how long it takes until the next call happens, and that would be an exponential distribution. Pretty sure. So the time until the next call would be distributed according to an exponential distribution. Number of calls in a time frame would be a Poisson distribution. So that's what I'm getting at. That's what I'm expecting to happen here. Okay. And different time frames would be different Poisson distributions because they'd be looking at a greater or smaller amount of time, and so you'd expect more or less of them to happen. Okay? And the time until like the 4th or 5th or 3rd call would be, there's a name for it, Erlang? Will be a sum of exponential distributions, which I think is Erlang. Okay. Just let me see if I've got this right. A gamma distribution is like an Erlang, but you don't have to have a whole number. Okay, good. Just making sure I've got it all sorted. Okay. So that means that exponential distributions are a kind of gamma distribution. Nice. Okay. Okay. So these are all the things that I'm thinking at the moment. Before I even start the problem, just wanted to think about what's related to this, because in probability you want to know the different thing. This is a situation about which you could write down all these different things, and each of those different things has a different distribution. Okay. So, okay. Probably no calls. Probably that no calls arrive in the first 2 minutes. So we get to decide how to do that. So that would be saying that either we could say that in the first 2 minutes the number of calls is 0, or the amount of time to wait until the first call is more than 2 minutes. We get to decide which of them we do. So, all right. Well, why don't we say on the first 2 minute time zone, time frame, and let x be the number of calls in the first 2 minutes. Then X will be a Poisson distribution. How does your lecturer write Poisson distribution? Does she write the whole word Poisson? It's the name of a person. The Poisson distribution counts the number of events in space or time. That's what it's for. So because this is a Poisson process, we can use the Poisson distribution to count the number of events in a certain time frame.
Yeah, but why do it? So my question is, she introduced it as we have like exponential distribution, that's independent, right? That's the distribution, like here, and we have Poisson between them. But why? I don't get it. How are they connected?
The exponential distribution is measuring the amount of space or time between one event and the next event. So the exponential distribution is measuring how long this is. But the Poisson distribution is picking a zone and counting how many of them are in that space. So they're doing opposite things. So the exponential distribution is measuring how long it takes until this one happens. The Poisson distribution is picking a length and counting how many events happen in there, which is the opposite thing.
Okay, so if you have one, the other one comes along as well?
What's that?
So if you have one of them, the other one should come as well.
And
we have exponential distribution, and instead we have a Poisson.
Yeah, there's always an exponential distribution along with a Poisson distribution.
Okay.
They go together.
They go together.
And they're measuring different things about that situation.
Yeah, same and different.
Yeah. So just a second. We're not going to be able to tell what kind of Poisson it is until we figure out what it is on average. So we expect there to be 3 in every minute, so we expect there to be 6 in 2 minutes. So your lecturer would normally call this lambda, I think? Okay. So they put Poisson brackets lambda. That's how they write the name of this distribution. Is that?
She puts T lambda, T is the minute.
Okay, well that's what I've done. I've done the time times that. But in my head, I'm just writing the mean in this spot. The mean number of events that I expect to happen in this time frame. Okay. So the probability that no calls in the first 2 minutes is the probability that the number x of calls in the first 2 minutes is 0, which according to a Poisson distribution is e to the minus lambda, is that right? Times lambda to the x over x factorial. Which is e to the minus 6, whatever that is. Very small. Okay, 0.025. Okay, so a very small chance of not getting any calls in those first 2 minutes. I could have done this a different way if I wanted to. I could have, instead of focusing on that first 2 minute time frame, focused on the first call and said, how long does it take until the first call happens? So I could have done, or alternatively, call and let t be equal to the time until the first call, and then t would be an exponential distribution with rate. Do you put a lambda in this spot? We don't put one, we don't put like a third, we put the 3. Okay, good. So because this is 3 per minute, the time will be measured in minutes. If I put 6 there, the time would have been measured in 2-minute blocks. So if I wanted it in hours, I would need to figure out how many there were per hour to do that. Okay. And then the probability no calls in first 2 minutes is the probability that t is greater than 2 minutes. It takes more than 2 minutes for the first call to happen. Which is the opposite of the cumulative distribution of an exponential distribution, and the upper tail, downwards cumulative distribution of that is e to the minus 2 lambda times the number. If you really want to, you could do it this way. If you really wanted to be all specific, this would be 1 minus p t is less than or equal to 2, which is 1 minus e to the minus lambda t. I'm just going to put the lambda t in there so you can do that. I'm going to put it there. That's like lambda t, which is either minus 6, which is what we had before. So either way would have worked. Okay? First call. Probability that the first call arrives after 2 minutes, that's the same question. No calls in the first 2 minutes is the same as saying that the first call arrives after 2 minutes. I'm just doing an example from the lecture slides. So. Sorry?
It's different because here it's going to be the same, but it's a bit different.
Okay. Right.
It's going to be the same.
But like never arriving at all is the same as arriving at, sorry. Maybe she's trying to get at what I just did by doing 2 different things.
I think you do it in a different way. You have to use non-intercepting property of the Poisson process.
Oh, okay. Right. That's interesting.
Stationary increment of the other one.
Okay. Well, let me just run with the next one. No calls in the first 2 minutes. And at most 4 between 2 and 3 minutes. Okay. Well, I would go Poisson with this. Let x1 be the number of calls in the first 2 minutes, and x2 be the number of calls between 2 and 3 minutes. So this is the idea here. There's 0 to x1 is the number here and x2 is the number here. Then x1 is a Poisson distribution with 6, which we've already seen. And x2 is a Poisson with 3, because that's how many we expect in a 1 minute time zone just here. So in 2 minutes I expect 6 calls. In 1 minute I expect 3 calls. And x1 and x2 are independent since they're non-overlapping time frames. And so the probability that I want because I can't be bothered writing it again. The desired probability is the probability that x1 is 0 and x2 is less than or equal to 4. Which would be the probability that x1 equals 0 times the probability that x2 is less than or equal to 4. And so this one is e to the minus 6, 6 to the 0 over 0 factorial. That's that one. And this would be the sum of several of them. E to the minus 3, 3 to the 0 over 0 factorial, plus e to the minus 3, 3 to the 1 over 1 factorial, plus e to the minus 3, going to go down the next line, plus e to the minus 3, 3 to the 2 over 2 factorial, plus e to the minus 4, 3 to the 4 over 4 factorial, whatever that is. So I did this because x2 is a discrete distribution, so to figure out the probability of less than or equal to 4, I have to add up all the probabilities of the numbers less than or equal to 4, which is 0, 1, 2, and... oh crap, I need a 3 and a 4. Right. Okay. Gotcha. And there's really no way around it. I mean, you can use a computer to do that for you. Something like R or MATLAB will be able to do the cumulative distribution of the Poisson for you if you ask it, without doing the individual things. But you won't have that in an exam, of course. Yeah, which is whatever it is, and, you know, a number. Okay. Okay, and I think the idea of that question is to point out that if you can separate it into non-overlapping time periods, you can just treat them separately. The important thing for me is realizing that there's two different distributions there. There's one for the first 2 minutes and one for the second 2 minutes. Okay. The fourth call arrives within 30 seconds of the third call. Okay. So two ways to deal with this, but it feels to me like we're measuring time here. So just going to think about what this is doing. Here's time, there's the first call, there's the second call, there's the third call, there's the fourth call, and we're saying that this time has to be less than 30 seconds. That's what we want, or equal to, I guess. Doesn't matter because it's a continuous distribution. Okay, so the probability of what happens after this is going to be independent of the probability of what happens before because of the memoryless property. So, I mean, I don't know how I want to, am I allowed to just say? I can just say that. Probably events after call 3 are independent of events before because of the memoryless property. And so therefore, let's let t be the time after the third call until the fourth call, and then that means t is going to be an exponential distribution with rate 3. It doesn't really matter what happens before. So the probability of desired probability is the probability that t is less than or equal to 30 seconds. So in our case that's 0.5 because t was measured in minutes. Okay, and so that would be the cumulative distribution, which is e to the minus lambda, like that. One minus e to the power of minus 1.5. So that's not too unexpected. I mean, if you've got half a minute, then if 3 calls happen in a minute, you'd expect 1.5 calls in half a minute. And so you would expect the first call to happen within that time frame, and so it should be pretty likely to happen. Okay. Time until the 5th call is greater than 2 minutes. Okay. So we could try and model the space between each of them and add them up, and that would be like some sort of fabulous Erlang distribution. Or we could say that in order to get greater than or equal to 5, in order for the 5th call to happen after 2 minutes, we have to have less than or equal to 4 calls in the first 2 minutes. So we could focus on the time between them or focus on the space of time that we're interested in. So we could say we want this to be after. So my 2 minutes, 2 minutes could be anywhere here. And then the 5th call would happen afterwards. So I reckon what we can do is we can focus on and go the probability that, and let x be the number of calls in those first 2 minutes. And then the desired probability is the probability that x is less than or equal to 4. Oh crap, I didn't write down what the distribution of x was. X would be a Poisson with 6, because we've already done that multiple times. Okay. So that would be e to the minus 6, 6 to the 0 over 0 factorial, plus e to the minus 6, 6 to the 1 over 1 factorial, plus e to the minus 6, 6 to the 2 over 2 factorial, plus e to the minus 6, 6 to the 3 over 3 factorial, plus e to the minus 6, 6 to the 4 over 4 factorial, whatever that is. I just can't be bothered calculating at the moment. So this should also be, or time until the fifth event, this should be an Erlang distribution with some parameters of some sort. Which I'm presuming is nearby in the notes. Chi-squared, Erlang. I'm looking for a box. Koshi. Here it is. So Erlang n equals 5, lambda equals 3. Okay, and so, yeah. That means, so we have f of t lambda cool, sweet. And so therefore the probability that I'm looking for, you want that to be less than or greater than 2, yeah? Is that what the question said? Greater than 2 minutes, yeah? Just a second. Time until the fifth call is more than 2 minutes, okay. One minus the integral from 0 to 2 of this. Yes! Which I don't care to do today. There we go. Lambda was 3. The n was 5. And that looks like, several layers of by parts. But if you have a good old graphics calculator like Desmos, which you won't have in the exam, but I really want to know what the answer is. Zero to 2 of 3 e to the minus 3 t times three t to the 4 over 4 factorial, which is 24 dt. It's apparently 0.28505. I wonder if that's the same answer as the other thing. So the other one we wanted, yes we can, from 0 to 4 of e to the minus 6 times 6 to the power of n over, oh no, not there. Ah, damn it. N factorial, yeah? Same answer! Yay! Cool. It worked. That's beautiful. Okay, I believe the Erlang distribution, but that is not what I would do in an exam because that integral does not look like fun. Cool. Okay. There you go. Is that sufficient to help deal with the sorts of situations you might come up with in that? Two people who asked me to cover this? Not enough? Oh, okay. I'm sure someone did. Oh, that's all right. I'm not paying attention closely enough. Maybe that was Jake, whose name is now on the revision seminar for all time. Okay. Okay. Now, what were the other things? Right, you had one.
Yeah, so not anything sort of specific,
Yep.
but just with some like accounting questions that we could get. So
Yep.
like, fundamentally understanding's fine, but like obviously there's like an infinite amount of like things she can throw at us, and sort of like breaking it down to make sure we can tackle it, I guess. Because like it's fine, okay, like what are the probability of getting like a full house? Like I can sort of practically understand that, but like obviously she doesn't throw anything at us in that capacity. Like with the assignment, I went through the assignment, like the cover balls and stuff like that. It's just like stuff we haven't seen.
Mm-hmm.
Sort of how to go about.
Cool. All right. That's going to be tough. I'm going to give some thoughts on it. Counting can be difficult. I call this, lots of people call this area combinatorics. So if you ever want to Google problems, you can Google combinatorics. Which is the study of combinations of things. I call it creative counting. And I find that the most successful thing I've ever been able to do to make sense of these things is to tell a story in a time order of events that produces the object that you're trying to make. So I need an example, but I can't think of any off the top of my head.
Gave a hard example in the assignment. Do you want that?
Sure. So you think about things where you're picking things out of containers and then arranging them and...
Yeah.
Yeah, I don't know what any of the poker hands are, so that doesn't help me.
Assignment. Oops. Sorry. So it's going to be here. Assignment.
So I'd like to hope that if she did poker hands, she would tell you what was in it. Because that is not useful assumed knowledge. Not everyone knows what the poker hands are.
I don't know how to go there.
Probability of a nothing connects in Mahjong, I might be able to do. Though that would be really low. Like on the first draw, yes.
Yeah, it's going to be... I think this was the fourth one, Ellie and the Boaz. Shameful. I think this one was the hard one.
Oh yeah, sure.
Yeah.
Sure, okay. All right. Can I borrow this for a second? Just
Yeah, so you just have to be touching it otherwise.
Yeah.
Yeah.
Actually, do you know what? I think it might be more productive for me to Google combinatorics problem and pick a new one.
I think it's better.
Do you have any insight into like how much before, like how much did you get will be given in a question? Like I know you said she's going to give it some.
Yeah, I mean, I don't know. I feel like anything, I feel like any formula that she hasn't proved, she's probably going to, well, she's probably going to give you. That's my expectation.
She hasn't proved the explanation.
No, well, the
I think that's the...
standard distributions with names, you just have to know their probability density functions.
So we get a formula sheet.
You get a formula sheet?
Yeah.
Okay.
Yeah, but just in terms of stuff like I don't know, for example, with
No.
Yeah.
And the fact that she's given you a formula sheet tells me that she's not interested in you remembering random crap. Yeah. Yeah, that's my expectation. So, so there you go. So she's much more interested in you being able to deal with things than remember them. But it's not the worst thing to have a general idea of what they should look like. Yeah. Here we go. This is the sort of thing you're talking about.
Yeah, pretty much.
Let's do question 3. We want to design a flag that can, that's this question just here. Yeah. So I'm going to do this and try and draw out the process that I'm using. But it's really hard to talk about that process without a problem to talk about. So we want to design a flag that consists of 3 horizontal stripes. The colour of the middle stripe should be different to the other 2 stripes. How many possibilities are there if the colours are red, green, blue, yellow, black and white? Okay. I'm just going to quickly write down the main details from that so that it's still here on the handout later. So 3 horizontal stripes. Middle stripe different to other 2. Colours red, green, blue, yellow, black and white. Okay. All right. So we have 3 horizontal stripes in a flag. Middle stripe different from the other 2. With the colours red, green, blue, yellow, black and white. I'm just going to call blue B and black K, if that's okay, just for the purposes of having one letter name for each of them. Okay. So I need to tell a story that contains all possible flags that will if I gave someone these instructions, would produce all of the possible flags. So I'm thinking about that this statement here, the middle stripe has to be different from the other 2. And I'm thinking that would be telling me that once I had chosen these 2, I need to choose a colour I haven't already got. But there doesn't seem to be anything stopping these 2 to be the same. Okay, so here's a story. I could choose a colour for the top stripe, and which means I can choose whatever I want. And then I could choose a colour for the bottom stripe, which means I could choose whatever I want. And then this one, I would have to choose something different to what I'd already chosen. And it seems to me that that would be a different number of choices depending on whether I chose the same colour twice or 2 different colours. Okay, so I've talked through how I'm going to do this, and so this is my story. So it looks like my story is going to be different depending on whether these are the same or different, so I'm going to take that back to an earlier part of my story. So this was my original story. Choose the top stripe. Choose the bottom stripe. Choose the middle stripe different to the top and bottom. That's a story. Okay? So, cool. And so I could tell that story. But this part here, 3rd step, this step is different. Depending on the 2nd step. Depending on what I chose, whether I chose it the same or different to the earlier colour. Okay, so it looks like our story should actually be choose whether these 2 are the same or not, and then choose what they're going to be, and then choose the 3rd colour. Or even better, just choose whether there's going to be 2 the same and 1 different, or all 3 different. Okay. New story. Three different or two same in the middle different. Okay. Okay, and out of those two stories we get two different things. So with three different, let's see, we could choose the top one and then the bottom one, then the middle one. And with two same, choose top and bottom because they're the same, and then middle. Okay, cool. So if we choose the top one, there's how many colours? 1, 2, 3, 4, 5, 6 colours. And then the bottom one has to be different, so there's 5 choices for what the next one is. And then the middle one has to be different to those, both of those, so there's that many. So every choice for the top colour has 5 choices for the bottom colour. No matter which one I pick first, there's still 5 different colours I could choose for the second one. And every pair of these, there's only 4 left to choose from the next one. So since every one of them has the same number of choices for the one after, I can just multiply them. So the top and bottom, there's 6 colours to choose for the top and bottom, and they're the same. And then the middle, there's 5 choices to choose for that. So it looks like the total is those two things. So 6 times 5, which would be 30 times 5, 150. Apparently. So it's very hard to teach this. So what I did was I tried to tell a story that made sure that I didn't cover anything twice and I didn't miss anything. And I was literally thinking about the instructions for telling someone how to make these things. And when I got to my story where a step depended on the previous steps, I had to separate them into 2 different things so that I could add them. I do have an alternative way of going about this problem. I think that's 150. That's 30. That's 20. 120 plus 30, yeah, okay. Or what I could do is I could choose the middle one first and then choose the other ones to be different to it. Choose my middle one, which happens in 6 ways. Choose the top, of which there are 5 ways now, because I can't use the colour that's already chosen for the middle one. And then choose the bottom, which is still 5 ways, because I'm allowed to choose the same colour for the bottom as the top, but I'm not allowed to choose it to be for the middle. So there's still 5 colours left, because we already used a colour. And we can reuse that second colour if we want. And so the total ways is 6, and then each of those has 5, and then each of those has 5, which is also 150. So this one's a little bit quicker if I had thought about it more carefully. Okay. So, have we learned anything useful from this example yet about how to make these choices? Yeah. Let's do another one to see if we can... That's what I want. Don't like ones that have horrible gendered stories. trying to find one. This one is not necessarily the best list. That's an actual textbook. Their answers. Of course not. That would be too easy. I'm trying to abstract ones. Let me just trying to abstract which ones are going to be useful to actually going to have combinations in them. Just a second. All right. Let me do this example, which I know what it needs because I've thought about it before. Okay. Suppose you have a televised singing competition. Here. Suppose you have a televised singing competition with 30 contestants. And 12 must be chosen to go to the live shows. Okay, these people will be announced one by one on the show. If Johnny, who has the most compelling backstory, has to be chosen, and it has to be announced within the last 3 in order to increase the suspense, how many possible announcements are there? Okay, so 30 contestants, 12 chosen. Yep. Johnny's in the last 3. And how many choices? All right, that's the essential information. 30 contestants, 12 are chosen. Johnny must be in the last 3. How many choices? Now, the fact that there is a last 3 tells me that this list is in order. Otherwise, there wouldn't be a last 3. So we have to come up with a story that creates this list. And there are in fact many ways to do this one, and they're all correct. So I know that there are for my 12, I could think about the 12 positions that I need to pick in my list. So I could actually just choose them in order, right? Choose the first one. Choose the second one. Up to choosing the 9th one, right? Because Johnny's in the last 3, right? So I can choose whoever I want, but not allowed to choose Johnny for this one. And then once I've chosen the first 9, then I need to choose, well, let me say, I can choose the next one who's allowed to be Johnny. And I could choose the next one, and if I didn't choose Johnny before, I'm allowed to choose Johnny now, and if I didn't choose, oh crap, that's going to turn into lots of different possibilities. So I could choose the 10th one, and I'm allowed to choose Johnny now. But then if I did choose Johnny, then the other 2 obviously don't have Johnny, and I can have whoever I want. But if I didn't choose Johnny, then I have to choose Johnny the second time, and if I didn't choose Johnny, then I have to. It's too many possibilities. So I reckon what I should do is choose which position Johnny's in. He's either in the 9th, he's either in the 10th, 11th or 12th position, so I could choose which position he's in. So choose which position for Johnny, either the 10th, 11th or 12th, and then choose the other two people. The first missing spot, and then I wish I had fished it all, and the last missing spot. Okay, so that's one way of doing it. So for the 12 positions in the yeah, I really need the space. Sorry, I'll put it on the next page. Okay, so for the 12 positions in the list, we haven't done anything there, we just set it up, so we haven't done any counting there. If we choose the first person who isn't Johnny, that's 29 ways. Because there's 29 people who aren't Johnny, and any of them can go in that first spot. And no matter which person I put in the first spot, there are 28 people left to put in the second spot who aren't Johnny. So when I get down to here, I've already chosen 8 people, so there's 21 people left to choose for the next one. 9, 8, 7, 6, 5, 4, 3, 2, yeah, 21. So I need to choose which position Johnny's in. Oh crap, I didn't end up with any choosers, I'm sorry. Which position Johnny's in which case there would be 3 choices for where Johnny could go. And then after I put Johnny in a position, how many people have I already put in? I put 10 people in. Haven't I? I put in the first 9 people and Johnny, that's 10 people, so there's 10 people left, 20 people left. And every stage of this story, there's always the same number of choices for the next step in the story. I don't have this thing where if I make a decision, it changes how many things are going to happen at the next level. And so I can just multiply them all together. Beautiful. Fabulous. All right. Does your lecturer do direct permutations from like straight up, or does she just do choose and arrange? I don't know what options she uses in her counting. Because if I look at this bit, that's 29, that's heading towards 29 factorial. But I have to divide by an 18 factorial, so I could do this as, which is a perfectly good, simple version of that, which is whatever it is, it's a very large number. Or, the other way of doing it is I could choose which 11 people are going to go with Johnny. So this is a different way of doing it. I could say, well, choose and I could choose where Johnny is in those last 3 positions. You know, 10th, 11th or 12th. And I could then just arrange everybody else in the remaining 11 positions. So the number of ways to do this is 30 choose 11. Is that how your lecturer writes choose? And the number of ways to do this is 3. And the number of ways to do this is 11 factorial. Not 30, there's only 29 because this isn't Johnny. Right, good. Allow me to choose Johnny in there. And so the total number of ways is 29 choose 11 times 3 times 11 factorial, which is the same thing, because this is 29 factorial over 11 factorial times 18 factorial. So the 11 factorials cancel. I quite like ones that where I go choose and then arrange. I kind of like those stories. Okay. I wish I had a really nice, complicated one that was really hard. Let me just try one more time to find one. Yeah, this is not the right one. Let P and Q be two tableaux of the same shape corresponding to the permuting G under the Robertson-Suggestion-Knuth correspondence. This is not the right kind of page to be using. No. Let's do number 18 there. I'm going to make one up based on that. I can't see both at once. All right. If I consider a circular table, have to sit next to each other how many ways? Okay. So all right, so cool. I guess this is where I have to start thinking about it. So it probably doesn't matter where Alice and Bob sit around this table, because I could just look at the table from another direction and it wouldn't really be different. And so I just need to choose where they sit, and I suppose it matters if Alice sits on Bob's left or on Bob's right, so we could choose what order they're sitting in, and then we have to fit the other three people at the table. So that's a good story. So choose which happens in two ways. And then I would need to choose where everybody else sits. And I guess once I've chosen where Alice and Bob are, these are perfectly ordered. It matters who sits next to Alice and who sits next to Bob, so I need to arrange the three people who are left. Because that's how the number of ways to arrange three things is 3 factorial. Okay, that was easier than I thought. 3 factorial is 6. Oh well. 10's friends sit at 2 tables. Alice and Bob sit at the same table, but not necessarily together. Okay, now let's see how many ways there are. So, just a second. I guess I need to choose 3 people to go at the same table as Alice and Bob. And it probably doesn't matter which table is which. So choose. And so that would be 9, choose 3. That's how many ways there are to choose 3 people to go with Alice and Bob. So arrange Alice and Bob's table. Well, I guess that would be like 5 factorial, except it doesn't matter which way round it is. So I'd divide by 5, because I could, all the rotation, no, just a second. Once someone sits down, everyone else can sit relative to them. So any one person sit down. So this is the sub-story. First person sits. Maybe it's Alice, it doesn't really matter. And then 4 people arrange relative to them. So this first person sitting down doesn't really change the arrangement, because it doesn't matter where they sit, because you could just look at it from another direction and it's the same arrangement. And so 4 people arrange relative to them. That happens in 4 factorial ways. And then arrange the other table with the same reasoning, which would be 4 factorial ways. And so the total would be that. That's what I reckon it is. I don't know if I want to make it any more precise than that answer. Well, let's try it. Sorry, you probably do it as 9 factorial over 3 factorial, 6 factorial, don't you? Sorry. I find it easier to do it as 3 factorial on the bottom and then 3 factors on the top. So that would count with most of that to be a 4. Whatever the number that is, I don't know if that's worth going any further. If I had a couple of weeks, then I would sit down and think of and find problems that require you to think through various different options. Because the harder ones are the ones where no matter how you do it, you have to separate it into 2 possible things and do them separately and add them later. Yeah. I'm sure there's another way of doing this. Because this calculation here tells me that there's probably another way. I could sit Alice down and then choose out of Alice and Bob, and then choose 9 people to go with Alice and 8 people to go. And there's 9 people who can go with Alice and Bob, and 8 people who can go with them, and 7 people who can go with them. Really not sure what's going on there. Just thinking of a different story. So usually if you can argue a story that produces all of the arrangements you want, it should work. My recording's going to run out in just a minute. Yeah. I don't know if I can extend it. All right, anything that I haven't talked about? Drop-in centres open all week. Feel free to drop in and chat. Where did what? This 9? Oh, it should be 8, shouldn't it? Should be 8. Well done. Because there's 8 people other than Alice and Bob. Yes. Well done. Okay. 8 people other than Alice and Bob because there's 10 people total. I can add. Okay. Yeah, you can always talk about any of these things in the Maths Learning Centre. There's enough of you there at once, then we can have little mini tutes, and I'll try and group you together. Okay.